Alrighty. Hello there, everybody. Hello and welcome back. We are live. Say hello in the comments if you're here. Let me know who's here. Thank you, everybody, for being here. Let me know, make sure that you can hear me as I get all set up now. Please excuse me. Diego, David, Lily, hello, everybody. Glad you guys are here. Let's get this situated a little better, if we're lucky. Jonathan, Alexandro, good to see you guys. Well, not really see you, I guess, but I'm glad you're here. Hello, everyone. All right, seems like that we can see that okay. Thank you guys for tuning in. How is everybody doing? Let's start with that. Tell me about life. I want to check in with you guys. Tibbetts, good to see you. Let me know, how has the past couple of days been? How have the past couple of days been? I want to check in on you guys and see how you're doing. I'd like to hear from you about how the e-learning has been going and about what you guys are up to in life. And Pack, who gave Pack? No. Who gave Pack the link to this? Who did this? I can't believe you guys have done this. Well, you're welcome to join in, Pack. I'm glad you're here. We're going to talk about circuits and physics later, so thank you for being here and joining in one way or the other. It's good to hear from you, Pack. I actually did miss you. On a scale of 1 to 10, it was about a 2, but that is missing you. Technically, I missed you a little bit, so I'm glad you're here. Yeah, thank you for that. What do you need help with? What do you need help with? I am here in the chat and in the stream to answer questions if I can. Talk to me. Diego, I'm glad you're decent. That's really good. I'm glad to hear that. I know these are trying times. It's difficult for me too. Pack, I'm doing all right. I'm doing good. Yeah, no, thank you for asking. I'm doing fine. It's, doing this, I really enjoy being able to spend some time with you guys here. Let's not forget to get those phones on Do Not Disturb. I know it's hard to believe, but it actually does exist. It's a thing. So let's go ahead and turn that on so that we are not distracted during this time together and we can devote our full attention to each other. Like I said, I miss you too, Pack, about 2 out of 10, but technically you're still on the scale, so we got there. But what do you need help with? You said you need help. What's going on? Why are you crashing my physics live stream? Coming in here and just throwing down. And by the way, for everybody, I really appreciate everyone who is here right now to join us. I would ask and implore you, beg you, perhaps, to please share this out with people who are not here right now. So I could keep spamming you guys on Google Classroom all week long. But here's the reality. If you are sending this to each other, the results, I feel like, are going to be a lot better. So I would really appreciate if you guys could share this out with people. It doesn't have to be people who are in my class necessarily, as Pack is evidence to us right now. I just would love to get some more people on this stream, and so I really need your help in promoting it. Please send this out to your friends and let them know that this is happening right now, because that's going to, I think, get a lot more viewership than if I just keep spamming it out there. So I will not mark you tardy, Nikki. I wouldn't dream of it. I'd be too afraid of the Wooddale police coming to my... I'm kidding. So, Pack, you said you need help with the math. We are definitely going to get into math a little bit, but this is a physics live stream, not a chemistry live stream. The chemistry live stream was this morning, my bud. Unless you're taking physics too. Are you taking physics with Barry right now? I thought you were in chem. So you got me kind of thrown for a loop here. But if you need help with the chemistry math, then what I'm going to suggest you do is actually tune in to the chemistry live stream tomorrow, and I will email you that invite pack so that you can get on there too. So that's something. Why did my watch just buzzed on me? But that goes down at 9:30 pack. So I'll send you an invite to that when that goes down. For everybody else, um, how are you doing? Uh, let's hear from more than just Pack, this random chemistry student who's not in physics at the moment. I'm kidding. I'm giving you a hard time. But like I said, share this out with your friends. Let them know that this live stream is happening. And tell me how you guys are doing. Like I said, Diego, I'm glad to hear you're doing decent. I know these times are not always easy. All right, Pack. I will catch you later then, buddy. I'll email you the info on that. And I want to know, I guess, are these live streams helpful? Do they give you at least something to do? You get a chance to, I don't know, interact a little bit, and that's great. Um, that's awesome, Nikki. I have played surprisingly few video games. I actually am a little bit disappointed in my amount of video game playing time. And we're still going to have to stream Over the Hedge together at some point. But I realized that there might be some legal implications to that. So I want to be careful with where I go with streaming, actual motion pictures. It's not out of the question that I could stream some Rocket League, although you would be utterly embarrassed by my performance in that realm. But one thing that we're looking up, I'm glad to hear that this is good. Thank you guys for chiming in and saying that in the chat. I really appreciate that. One thing that I am going to probably be doing very soon is we will have a Zoom conference where everybody will be able to be on camera if you want to be. Okay, if you don't want to turn your camera on, or if that little piece of tape that you put over your Chromebook camera 2 years ago is like impossible to get off at this point, then that is totally okay. You can be on just with sound, or you can just be muted entirely and just watch and listen. That is fine. But I think if we do that where we have the opportunity to all be in a video chat together, I think that would be pretty cool and an even better way to interact than this right now, which is just me staring at a webcam and hoping that you guys are listening. So the Zoom thing, Zoom video conferencing is in the works. I could probably be ready to do that as early as Friday, maybe even tomorrow if we're ready. But Kevin, hello, good to hear from you. Good to hear from you. The Minecraft server, I would like to definitely do the practice problems. Hannah says helps. I'm glad. Kevin, you can video chat not in the bathroom, please. That is the one stipulation that we would have, is it would be recorded. So I would ask that everyone behaves appropriately, is dressed appropriately, just like if you were coming to school on a regular school day. Even though we're all not at school, if we could have the same level of decorum and the same level of the rules still applying there as we would on a video chat, I think that would be probably the best way to go about things. And as far as everyone talking at the same time, Lily, that is 100% a possibility. I don't know. It's a little harder to deal with than when you're in class because there is some slight lag in between people talking, but I think we could handle it. So, hey, you know what? We're going to try it. If it crashes and burns and it's terrible, then it's terrible. But if we try it, we try it. It is what it is. What is that? Is that a new meme now? I don't even know. Who said that? What's the origin of it is what it is? I mean, it's a common phrase, but I feel like you guys have some inside thing going on right now that I'm not privy to. TikTok. TikTok. Okay. I don't know how we're really going to survive as a species. Now with everybody cooped up inside, TikTok is going to take over the entire world, and it'll be over for everybody. Just done. That's it. Some news today that you might be interested in hearing from the news desk. I'm just kidding. This is blank. I don't actually have any news in front of me. Um, the Jewel is doing Tuesday mornings and Thursday mornings from like, I don't know what the times were, 7 to 9 a.m. or something like that at the Jewel for senior citizens and people who are at risk only. So let your grandparents and anyone else know, spread the word that if they need to go out and get groceries, first of all, y'all should go out and pick up some groceries for them. But if they need to go out, they have a special time now at Jewel where they can, not that Jewel, the Jewel's Osco, okay? They have a special time now where that's for seniors only, where they can go and do their shopping where it's a little bit less busy. And that's probably a really good thing. And Target is also doing that on Wednesday mornings. So it'll be Target on Wednesdays and Jewel Osco on Tuesdays and Thursdays. So you might want to spread the word around about that. That's some news that I heard today that I think is good. It is what it is, a TikTok. You need to be in the know to know you know. Yeah, Kevin, I know. You know, they say to be in the know, you have to actually be in the know and not that. All right, well, that was a good effort. I need a button to click to rewind 5 seconds and reverse what I said when I make mistakes, but that's fine. So if there's nothing else, should we get down to business with physics? I think it's about time. I stalled for long enough. Let's do it. So here's the circuit that I put on Google Classroom yesterday. I'm going to take you guys a second to get your notes ready, to get your calculators ready, and to get anything else you need ready while I blow my nose, because apparently I'm still not feeling well. And I'm back. So this is the circuit that I put there yesterday. I would like to solve it with you guys, or hopefully, since I asked you to give it a try, you have already solved it. I would like to know where you're at. Have you solved it? Did you get stuck? This is the actual physics portion of the live stream now. So if you have not done this circuit yet, I'd like you to start, and perhaps we could crowdsource the strategy, and you guys can tell me the steps that you want me to take. All right, Lily, I appreciate that. That's cool. I want you guys to crowdsource the steps that we should take, and then we'll see if we can figure this out together. So I will not ask what you did, Lily, but I will ask, what do you guys think the first step should be? And I did give you guys a hint on the document that I actually posted in Google Classroom. So there's a hint out there that has the first 4 steps. All right, Hannah, I appreciate that. That's okay. You know what? Trying is what counts. The fact that you tried is what matters in this context. So that's cool. I'm totally cool with that. What's the first thing that I should try to do with this circuit, by the way? So that's what I'm asking. That's the question that's out there right now. Crowdsource this with me. What is our first step? And this is generally the case when you have all the resistances of your resistors, and that is to find the total resistance. So that's correct. It is to try and figure out what the total resistance is of the circuit. And so that's the first thing that we are going to do. So in order to do that, we have to notice that we've got one resistor here all by itself, and then this parallel branch. This parallel branch has 2 separate branches. We'll call them the top and the bottom. The top branch is simple. The bottom branch is not, because it has 2 resistors in series with each other. So what we'll need to do is combine those series into a single equivalent resistor R34. So the resistance of R34, since they are in series together, is, you can say it in the chat. I have to wait because of the time delay. But I will wait. I need something to do while I wait for answers. Don't I? It is 6. That is correct. I wonder what I could do while I wait for answers. Good job, everybody. It is 6. That is the resistance of the equivalent resistor R34. So with that being said, I could like play with blocks or something. I've got a guitar back there. I could grab that. Maybe you got a piano there or something like that. I don't really know what that means, Kevin, but if I think I know what it means, then I'm going to have to say that's probably not the appropriate response that I was looking for at the moment. But I'm not sure. So the two resistors combined together are 6 ohms because they're in series, 2 and 4. Then what we can do is I'm actually going to erase this, put in that equivalent resistor there, R34. And the next step is we still need to, the dog or the baby. Yeah, the baby is taking a nap right now. And the dog is, I'm not sure what, probably upstairs napping as well. But what's the next step now that we have taken R3 and R4 out of there and combined them into a single resistor? What do I need to simplify next? And this is a tricky question, but I want you guys to think about it for a second. Inverse ohms. Why would I want to inverse the ohms? What do you even mean by that? The inverse ohm law, what am I going to be doing if I use that? So that's the correct, you guys are right, but be specific for everybody else in the chat. What are you actually doing to the circuit by taking the step that you guys are talking about there? Like 0.86, Nikki, is what? What do you mean by 0.86? The inverse of R2 and R34, then the inverse of the total. Yeah, okay, so what you are doing then is you're really taking this parallel junction and you're smashing it into a single equivalent resistor. Okay, so what you're doing is this parallel junction, we're going to take and make into an equivalent resistor, which we're going to call R234. And then we're going to rejoin our circuit and proceed. So essentially what you're doing is you're eliminating the parallel part of this by taking R2 and then the equivalent R34 that we made and smooshing those together into a single resistor, which is now R234. So the resistance of R234 is equal to the inverse of R2 plus the inverse of R34, and then we're going to inverse that whole thing. So that is the inverse of 1 plus R34. Remember, that was the equivalent resistor that we made at the beginning, because R3 and R4 were separate. We squished them together into R34, and that ended up being 6. Then we'll take the resistance of that whole thing, and I think you guys have got it right. Hey, Barry! Welcome, sir. I am glad you are here. This is exciting. We have an actual celebrity on our channel, guys. You were right earlier when you said 0.86 for the resistance of this guy, by the way. So good job on that. Whoa, 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 Kevin. Kevin, be nice. You're in the presence of a god, okay? An Adonis, a regular saint, someone who has chosen to bless us with his presence and then maybe immediately left. I actually have no idea if he's still here or not. But that is a good point that he brought up. Because of the situation that has happened, obviously there's not going to be a midterm before spring break. I'll give you guys more details on how this is all going to play out at the end of today's live stream. So if you want to hear those details, you're going to have to stick around for the stream. Yeah, back to our circuit for now. We've got our parallel branch that we started out with has now been smooshed. And I wonder if I have the drawing of the circuit that I made yesterday that I scanned, because I scanned it. Where would it have gone? Organization is the best. I like to be organized so I don't lose my things. Well, that stinks. I don't know what I did with it. But you guys can reference the original circuit on Google Classroom. I have that open on my second screen here right now in the background so that I can reference it. But now what we've managed to do is we've managed to get that parallel branch completely broken down into a single resistor that happens to be in series with R1. So now if we were to turn to the original goal, which is to figure out the total resistance of this circuit, it's quite good that we only have two resistors in series with each other, R1 and this fake imaginary resistor that we've managed to put together, R234. And so when we add those together, the total resistance of our circuit is 2.86. And I would like you guys to verify that and send me a thumbs up in the chat if you are still with me and if that makes sense for everybody, while I attempt, perhaps unsuccessfully, to fix the angle on this a little bit so you guys can see it better. It's probably going to topple on me. I know the red doesn't show up incredibly well, but I think you can see it well enough. I hope you can see it well enough. I'll stop using red. No more red. Okay, so now that we've figured out the total resistance, what are we going to do next? Or are there any questions on how about we got to figuring the total resistance? I think what we need while we wait is like background music. Kevin, I'm not sure what that means. Background music, though, while we wait. What is R1? R1 is 2 ohms. It's right there in series. What's hot? What do we want to listen to? WTW. Okay, so that's actually a good question that somebody asked. For the total resistance, why can't you do R1 plus R2 plus R3, 4? Miss Lem is here too. Oh my gosh, we've got more celebrities. Hi, I'm so excited. All right, so Hannah, really good question. Why can't we just add the resistors up? Ooh, good point, Mr. Barry. Good point. There's only one way to find out, right? We'd have to test it. We'd have to test it. Yeah. All right, but Hannah, why can't we do just add up all the R1 and then what we had was R2 and then R3, 4? So if we go back, I'm going to have to draw this. We had R1 here, and then we managed to make R2 and then R3, 4. Why can't we just add up all three of those resistances in order to get the total resistance? I think that's what Hannah's question was asking. And that's a good question. So why is that, right? So I'll leave that open to you guys in the chat to try and answer. Why can we not just add all three of those resistors up now that we did it? Gonzalez, you're about to get muted, by the way, man. You're starting to get a little towards the scale of inappropriateness. So we'll try to answer that question. Why can you not just... Uh-huh. Gonzalez is in timeout now, so he can wait until he comes back, and we'll see how that goes. Thank you. I know. So, story behind those is we went and got my daughter a passport today, because she is planning on taking a trip this summer. I have no idea if that's actually going to happen or not. It's not looking great right now. But be prepared. There's a chance it could happen. So we went and got my daughter a passport, and we needed both of our driver's licenses. She is not too young to go anywhere. In fact, it is not. She's not. Where are we going for... this question is still not answered. Hannah's question. So why can't you just add up all three resistors, guys? What would be wrong, per se, about trying to do it that way? What we did was we combined R2 and R34 together first. So we created this circuit where we had R1, and then this thing that I've called R234, that were just in series together like that. Why was that step necessary? Why couldn't we have just skipped that step? Also, what I wanted to ask was, what is the next step? Where are we going to go from here? So what information do we know? We can figure out, if you look at the table, what would we be able to fill in? All right, so we got a potential answer for that first question. That's exactly right, Nikki. You can't combine resistors that are in two different types of arrangement. So we've got resistor 1 is actually in series with this parallel part, resistor 2 and resistor 3. You can't add resistors when they're in separate types of arrangements. So when you have all your series resistors that are just in series together, you can add those together. When you have resistors that are in parallel together, that's when we're using this inverse law for parallel resistors. So you can do that. But when you have a mixture of series and parallel, you can't work with that. You have to simplify it so it's either all series or it's all parallel. But you can't mix and match with both. So Hannah, what we had to do was we had to take that part of the circuit that was still in parallel, and we had to collapse it down into what its equivalent resistance would be for this branch of the circuit. Now we've got that's just in series with R1, and we're good to go. So I don't know, Hannah, please chime in and let me know if that answered your question. Because Diego is right, that is the next step. Awesome, I'm glad to hear that, Hannah. The next step is to find the total current going through this circuit. So we're going to use Ohm's Law to do that. Oops, I typed the number in wrong. And we've got 4.12, or no, sorry, 4.20. Yep, 4.2 for our overall current. Awesome. And now that we have found that overall total current, what are we going to do next? Keep it going. So Mr. Barry, if you're still here, if I play like the Jeopardy music and it's copyrighted, Will they mute me like permanently? Like, what will have to happen to me? Will I be muted for life? This is what I want to know. How would I fill in the voltage, Nick? What would I have to do in particular to fill in the voltage? All right, well, I'm probably going to be copyright banned for life now, but it was worth the risk. So the voltage through R1. Okay, that's a good idea. We could find the voltage through R1, and that's a great point. But how are we going to do that? We don't have enough information on that table right now to just use Ohm's law. To just use Ohm's law. So we are missing something. What are we missing before we can figure out the voltage through R1? I'd like to see this music that YouTube has available. Add on there whenever I feel like, but what else do I know other than voltage? Because I don't directly know voltage. I'd have to calculate it for R1. But what do I actually know directly about R1 right now as it stands, guys? If R1 were 12 volts, if R1 used up all 12 volts, remember voltage is our energy, so I've got 12 volts of energy leaving the circuit. If all of that was used up by R1, then it would be 0 volts after, and there would be no voltage left over for the rest of the circuit, and that wouldn't be allowed because R1 is not the only thing in the circuit. I have to make sure that I have some energy left. Otherwise, I'm not going to be able to make it through the rest of this branch, and that can't happen. So I can't assume that R1 would be 12 volts because I only have 12 volts total. But, Diego, you're correct. The current I can assume. Careful. What is the current, Nikki? What's the current coming out of the battery? How many amps here are coming out of the battery total? So as we leave the battery, we've calculated that we have 4.2 amps worth of current that are going out there, right? And those 4.2 amps of current are going to go around the circuit, and they're going to get through R1. And so R1 is going to receive 4.2 amps of current. Now, with that knowledge, what is the voltage of R1? You don't need a calculator for that, actually. Wait a minute. Time out. V equals I times R. So what is 4.2 multiplied by 2? You can't necessarily make the assumption that it's just going to be half of the voltage or anything like that. Right. You have to use the actual Ohm's law. So it is 8.4 volts. We got that by actually multiplying because we've got Ohm's law, V equals I times R. So you have to make sure that you're careful about that. Now that we have that, though, now is where life gets a little bit tricky. And I think this is where my next hint was to find V2 and then find V34. So what I'm going to do is I'm actually going to go back to the way the original circuit was drawn, because I want you guys to be able to see the original circuit as we work through this. This was R2, we had an R3, and we had an R4. So that's the way the original circuit was drawn. Now we know, as we've gone through V1, we've used 8.4 volts of energy. Here's the trick. How many volts of energy are left over? Having passed through R1, How many volts of energy remain? Because we have to go from 12 down to 0. So with that information, you can figure out another part of this puzzle. So 8.4 volts were used at, excuse me, R1. 12 volts total to start out with. And that leaves 3.6 volts remaining. That's exactly correct. If you do 12, the 12 volts that you started out with minus how many volts have you used so far? Well, you started out with 12 volts and you've used up 8.4 volts so far. So there are, of course, 3.6 volts remaining for use in the circuit. Now what that means is that no matter which branch you take, 3.6 volts is going to have to be used. Because after this parallel part is over, okay, after this parallel part is over, is there anything else in the path of the circuit, right? And the answer is no. There's nothing else in the path of the circuit after that parallel part is over. And we know when we get back to the battery, we have to have used up all our energy to get back to 0 volts. So I can make the assumption that each branch of my parallel circuit will have a voltage of 3.6 volts. And because of that assumption, I can say that R2 will get 3.6 volts of energy through it. Okay, so that's awesome, but here's the question. How does that play out for R3 and R4? R3 and R4 both cannot have 3.6 volts, right? Why? Because if you use 3.6 volts at R3, then 0 voltage would be left over for R4, and that wouldn't be allowed. You can't have 0 volts for any one component of your system, and series components would lower the voltage as you go through them. So if we use all 3.6 volts at R3, then we have nothing left for R4. That can't happen. R3 and R4 get 3.6 total volts to share. R3 and R4 should have a voltage total between them of 3.6. They get that to share. So we'll have to talk about that. That's not a problem for R2 because R2 is all by itself on that branch. So if you're going through, you go through R1, you use up your 8.4, you've got 3.6 left. Imagine you're a single electron traveling through this circuit. You go through the top branch R2 where you have now 3.6 volts remaining and you're going to use that all up. And there's nothing else in your path after you go through R2. So it's safe to say that all of the energy gets used at R2 because there's nothing after it. That's not the same assumption that we can make for R3. Now 1.8 is, I'm guessing you said that because it's half of 3.6, but that's not valid because the resistances of 3 and 4 are not the same. So we have a problem. Let's circle back to that. Let's first finish what we can knowing about R2. What else can we know about R2? What is the current through R2? Using Ohm's law, V equals I times R, then V divided by R, voltage divided by resistance is current. So we know that 3.6 amps get used at R2. 3.6 volts divided by 1 ohm is 3.6 amps. Okay, so the current through R2 is 3.6. Now voltage we couldn't figure out. We don't know what the voltages of R3 and R4 are, but what do we know about current? So let's think about this for a second. I really need like multiple layers of whiteboard that I could like a bunch of clear sheets that I could just like flip. That would be awesome. One day in my life, maybe I'm gonna have that. Or I could like use a computer or something where I could, whatever. But check it out. Let's talk about current. I was doing current in blue and I said that red was bad. Two good questions on the stream right now. R3 and R4 have the same current. Yes, that is exactly correct. R3 and R4 will have an equal current as each other. The only question is, how much will that current be? Well, check it out. We have 4.2 amps. 4.2 amps, current in equals current out. So 4.2 amps go through R1. 4.2 amps come into our junction here. 4.2 amps come into our junction. 3.6 amps go up to the top of the junction. So how much current is left for the bottom of the junction? It would be 4.2 minus 3.6 is what you meant to say, Diego. And that is exactly right. 4.2 minus 3.6 means that if 3.6 amps go up, then we must have 0.6 amps left over for the bottom. 3.6 amps on the top branch and 0.6 amps for the bottom branch. And Hannah was correct that that will be shared by R3 and R4 equally. So we can say that the current at R3 and R4 is the same. And now, Diego, you asked a question, would the volts of R4 be twice as many because its resistance is twice as high? And you are right. You can see that played out now if you finish and you do the math. 0.6 times the 2 ohms means 1.2 volts for R3, and 0.6 times 4 is 2.4 volts for R4. Twice as many volts for R4 as we had for R3 because the resistance of R4 is twice as big as the resistance of R3. So that's great proportional reasoning and proportional thinking. And by the way, I've said this before, I love circuits because they are self-correcting and self-checking. What is 1.2 plus 2.4? It's 3.6, which was the voltage that we knew had to be in this bottom branch of the parallel circuit. Whew! Drop the mic. That was a doozy. That was a tricky one. Let me take a second and see if there's any questions about any of the steps that we took. If there was any component in our V equals IR table that you were not sure how I got, say it now in the comments. Is there any part of this table that you're not sure where I acquired? And I'll go back and I'll ask the people who tried this. Lily, you said you had tried it. Hannah, you said that you had tried it. Were you close? Did you have some of the stuff right? Were you on the right track? Can you at least identify kind of where you went off the track and what the correct path that we needed to take through solving this was at this point? Good job, man. That's fantastic. I'm so happy to hear that. And that's great. I love solving these. I particularly love the satisfaction that I get when they work out correctly. It's always a great kind of feeling. So what else? Questions, please, in the chat. Questions, comments, thoughts? Messed up on the resistance. Okay, so then I would say that, but we did answer a question that you had about calculating the resistance, so I hope that helped. Okay, so Lily, that's okay too. And that's really why we're going to keep practicing, right? So for those exact reasons, we're just going to keep practicing as we go through this. And with that additional practice, you guys are going to get better at this, and it's going to work out. I do want to wrap things up here in a couple of minutes, but I'll take another second and ask if anyone has any questions, anything else that they want to talk about. As far as the circuit goes that we solved, I'm going to put another practice circuit on Google Classroom today, and I'll ask you guys to take a look at that too. And that's pretty much what we're going to do. We'll keep practicing circuits, and we'll try to do some other fun stuff as well. I don't think I could handle going through a full 2 weeks of live streaming just on circuits, so I'm going to try and think of some other different fun things that we can do together as well. But I wanted to kind of wrap that up here and see if there was anything else you guys wanted to talk about before we left. The one thing that I will talk about, Mr. Barry mentioned the midterm. So because we are not going to be able to give midterms with the way the school year has gone, All the tests we have given are going to be kind of upgraded as far as their how many points that they're worth in your grade. So instead of having a bunch of tests that really were just quizzes and then a midterm, it's just going to be the test grades. Um, and then the final exam is still going to be the same as it's been in the past semester. So if you get an A on the final exam, you get the A. If you get a better grade on the final than your current grade, I'm going to upgrade your grade. So all the things are still pretty much the exact same as they've always been. The only difference is we're not going to be able to do midterms because we just won't have time for them this semester with the way things have gone down. So I wanted to get that news out there to you guys. Again, thank you so much for being here. If I could say one thing about this, be kind to each other, treat each other with compassion and care, and together as a community, we will get through this together. But this is difficult for everybody, what we're going through. Everybody deals with this in different ways. No two people go through the same process as far as how they're dealing with what we are going through right now. And so understand the way somebody may be processing things and the way it may be affecting them emotionally might be different from the way it's affecting you. Be kind to each other above all else. If you need anything, questions, academic, emotional, any of those things, like I've said before, please don't hesitate to reach out. We care about you guys and how you're doing, and we want to make sure that everyone's okay. Thank you so much for being here. If at all possible, like I said, please promote this to your friends because it'd be really, really helpful. Hey, it'd be really, really helpful if you guys promote this to each other. Hey, buddy, because that is the number one way for us to get more viewers on the stream. And I would really love to see our numbers get a little higher since this is about half of our class right now. I would really love to see that get higher. So thank you everyone for being here. I really appreciate it. Spread the word if this is a good use of your time. This is 45 minutes that you weren't thinking about life and you were just hanging out together. That's 45 minutes that you're not bored, that you can be here with us. I really appreciate that. Spread the word. My dog says hi. Mo, give me kisses. Kisses. What? No kisses? I just got rejected by my dog. You all see that? I can't believe that. Is 2 o'clock good for everybody tomorrow? 2 o'clock is good for me if it's good for you. So I would say we'll keep it at 2 o'clock and we'll go from there. All right. Goodbye, everybody. It's good to see you guys. I will talk to you all soon.